welcome to this session on what plasma sensing reveals on the coating line. This is a co-presentation between SirenOpt, which is a company based out of the San Francisco Bay Area, developing cold atmospheric plasma sensors for inline metrology for battery electrode manufacturing, as well as the Technical University of Munich. Johannes will be co-presenting with me. He represents the TUM side of things. This is a collaborative work that we are presenting today between TUM and SirenOpt. My name is Parnika. I'm the head of product at SirenOpt. I joined SirenOpt about a year ago, and before that, I have 8 years of experience in the semiconductor industry. Johannes, would you like to introduce yourself?
Yeah, thanks. So my name is Johannes Lindenblatt. I'm a research scientist at the Technical University of Munich. My PhD was about the inline prediction of the quality of electrodes. And I'm very interested in this topic in the plasma sensing. So yeah, Monica, just start the presentation.
Okay, awesome. So before we start sharing our data with you, I'd just like to take a quick poll of the room. How many instruments or sensors do you need to characterize your battery electrodes right now? And can you put your answers in the chat and Johannes can read them out?
Yeah, feel free to just write down whatever you think is right at the moment. I know from our pilot line we have a lot of sensors, and it's difficult to measure the electrode quality. So, some guesses from you. Do you think is necessary to measure the electrode quality? As many as you got the budget for, yeah, that's a possibility to get as many as possible. And I think that's also a problem that you need multiple sensors at the moment. Yeah, so basically you need a lot of data to actually know your electrode quality. And now it would be amazing if you could gather this data with only one source. So yeah, Panika, I think we should start to present our data.
Cool. Yeah, I think so. The point was to motivate what Johannes already said, that right now you need a lot of different instruments and sensors to fully characterize your battery electrodes. And what we are going to talk about today is if you just had one sensor that could measure multiple properties, how would that change your life as a battery electrode manufacturer? So let me start with some backdrop of why I think battery manufacturers underinvest in metrology. So since I come from the semiconductor industry where we spend a lot of money on metrology and inspection, I'd like to just show some numbers on how different industries spend on metrology and inspection equipment. So you can see semiconductor is pretty high. We spend about 12% on metrology and inspection instruments and overall processes. Some other material intensive industries like aerospace and automotive are around 2 to 3%. And when it comes to batteries, even with gigafactories, the spend on metrology and inspection is only 1.5% of the total costs. This is clearly a very low number compared to other industries, and it shows up in very high scrap rates of these battery electrode manufacturers. So a new factory scrap rate can be as high as 84%. When you get to a steady state, you can go down to 8 to 30%. China leaders are at 2 to 3%. But it's still pretty high. And just this morning, we were talking about a fire in a BYD car, and BYD is clearly one of those China leaders. So there are still very significant consequences of high scrap and low yields and not checking your battery electrode materials early enough in the process. Another study reveals that every 5 cents per kilowatt hour spent on inline inspection can lead to savings of $7.5 per kilowatt hours in preventing field failure. So huge upside in investing early in metrology and inline inspection at the very early stage of the battery electrode manufacturing process itself. So what we are going to motivate in this talk today is that electrode manufacturing is the stage where a lot of defects start. And a lot of quality control right now is offline after the material is already moved through the line. And so that entire batch has to be scrubbed if some defects are detected. And if we started to do inline sensing, we have the opportunity now to control those parameters inline real time before we waste the entire batch and also reduce scrap. So some more numbers around how much savings we can get from having a full inline metrology deployment. So what you see here is that we did some back of the envelope math to show that you can get up to 91 million of annual savings per production line with full inline metrology deployment. These savings can be broken down into operational savings. So these are things like you can improve your overall yields, you can improve material efficiency, so now you don't have to do overcoating. You can reduce the number of cells per pack, so you do not have to account for excess cell margin. And then there are things like strategic upside, which are that now your cells can perform at a higher performance, and that you can charge extra for that. You would have a lower risk of recall, and you can account for that as well as accelerate overall time from going from pilot to production. So overall, this back of the envelope math shows around $91 million of annual savings per production line with inline metrology. And SirenOpt makes Plasma Sense, which is our inline metrology solution, which provides real-time, non-destructive inline measurement of multiple electrode properties and detects defects with a single measurement. So before I go into explaining what Plasma Sense is and how it works, Johannes is going to talk a little bit more about the cause of low yields in battery manufacturing.
Yeah, thanks, Parnika. So the crazy thing is that even though the battery manufacturers underinvest in quality determination, scrap is at the moment one of the main challenges for the cost-effective upscaling. So I think, in my opinion, it's maybe because there are so many challenges in battery manufacturing that the manufacturers just underestimate the quality control. So we have high energy and space requirements. We have like a very complex production chain. And these cross-process cause and effect relationships that are not determined at the moment, they produce these high scrap rates. And so the main issue is that at the moment, we don't know the quality of intermediate products, especially for the electrode. And one thing, how the quality control in the moment or at the moment in battery manufacturing is done is by the so-called traceability. Parnika, please. Yeah, thanks. So this traceability is at the moment the only solution to actually know the production quality. So you have to know exactly what are the sensor data or what are the sensors and what is the sensor data for every electrode sheet from the beginning, from the mixing till the end of the production line. And in a recent study, we've shown that basically with scrap material recovery, which is the main point or the main thing you can enhance, you would decrease the cost for a kilowatt hour from approximately $96 to $90. So you have a lot of money you can basically spare or have spare when you have the right quality determination. And the main problem is at the moment that you need this kind of traceability. So, and on the next slide, on the first figure, you can see the actual production chain. So this complex production chain, usually, as you probably know, starts with the mixing process, which is usually a batch process. Of course, you have a continuous extrusion, but in most cases, you still have batch processes. And then you go to the continuous electrode production, where the first process starts with the electrode coating. You coat on these thin metallic foils, and then you do the calandering process. And then you have the one process, the slitting, where you basically slit the mother coil into smaller coils, and then you have the cell assembly. So the main issue is that only in cell assembly you can get rid of the scrap, and then in the filling and the basically quality control in the end, you have such a long process chain with first batch processes, then continuous electrode production, and then discrete cell production again. And the main issue is that the electrode quality is very important. but you have these changeovers from continuous to discrete production, which complicates quality control of the intermediate product electrode. And the main issue is, especially in the calendering, deviations and defects in the electrode can damage the calender, so the equipment. And key battery characteristics like the capacity or the C rate, so the performance, they are very influenced by the electrode. So even small percentages of defective electrodes can result that the entire battery is basically scrapped. And this is the main issue why we need a better understanding of the electrode quality. So what we did in the past works. So here are some papers of me or my team. We need smart battery manufacturing at the moment. So we need multiple sensors per process that are used to create an electrode twin. So this is basically state of the art, I would say, electrode quality determination. And there you use different sensors, and then you have edge devices to combine all this data into one digital twin of the electrode in the production. And with this data twin, digital twin in the of the produced electrode, you can monitor a lot of different parameters of the produced electrode, and you can integrate multiple sensors. But you still need tracking and tracing. You still need all these sensors. You need all this equipment, and you need this kind of important data structure so that you can know the quality of your electrode. And when we look deeper into the different intermediate quality parameters, we can see on the next slide that the main issue is that at the moment we only know some quality parameters inline. So when we look at the process chain, starting with the mixing process, we have a lot of different parameters for the slurry, but they are all measured offline. Then we have the coating process, where we can only measure the mass loading and the thickness. Of course, there are two important characteristics of the electrode. These can be measured inline, but in the drying state, we have mechanical properties that are not possible to measure inline. We have the tortuosity, the electric conductivity, and all these processes, or these process parameters or intermediate parameters, are not possible to measure inline. And that is where our collaboration started, and where plasma sensing is a possible tool. And with this, I want to hand over to Parnika again.
Thank you, Johannes. So I think as Johannes motivated, right now there are a lot of properties that are measured offline and destructively, and Plasma Sense can measure multiple properties inline and non-destructively. So on the left, what you see is Plasma Sense Web, which is our roll-to-roll version that integrates with the electrode manufacturing machines. The big black mass in the center is the main sensor head, which has the plasma coming in and all of our detectors. I'm going to talk more about them in the next slide. And paired with Plasma Sense, we have our Plasma Smart, which is the decision-making software. So some of the decisions can be seen on the image on the right, where you see that we are revealing a wrinkle defect in a separator membrane. And on the right, we are doing some quality control by making comparisons across different batches. So overall, what this entire package gives you is real-time inline monitoring of several properties that overall, eventually, the more you deploy these sensors in line, can accelerate your time to market, increase yield, improve performance, and reduce safety risk. So let's dig into how the Plasma Sense sensor works. So at the core of it is cold atmospheric plasma. So it's cold because it's room temperature, atmospheric because it's atmospheric pressure. So these are really gentle, low energy plasmas compared to, let's say, the semiconductor plasmas or the plasma that most people associate with as nuclear fusion or the sun. So compared to those, these are very, very gentle plasmas. We control the power delivered to the material real time with real-time feedback control. And so that's how we ensure that the plasma is super gentle on the material. So this plasma, right now we have two gases, helium and nitrogen, that are available to generate the plasma with. So these plasmas, when they interact with material, that interaction is very rich. It has thermal signatures, optical signatures, as well as electrical signatures. And that is the essence of the metrology. So what we do is that we have three kinds of sensors. We have an optical emission spectrometer, we have a thermal camera, and we measure current going through the sample, which forms an electrical circuit with the plasma itself. And because of these three modes of detection, we get very rich raw data from our sensors. So on the bottom panel, you see examples of the three kinds of data that we are collecting. So in the optical emission spectrometer data, we are collecting several peaks of different wavelengths, and we monitor how these intensities of these peaks are changing as plasma traverses over the material. The thermal camera captures how heat is propagating through the material surface as it is being heated up by the plasma. And the voltage and current probes measure current going through the sample. So here again, for every single measurement point, we apply close to 200 electrical waveforms, and those measure a very rich data set coming from the material itself. So that correlates directly with the material's electrical properties. So now that we have this really rich raw data, we collect close to 200,000 raw data numbers per measurement location, as I said. And on any given sample, you will have several hundreds of thousands of locations, depending on how fast or how comprehensive you want to be in your scan. And so let's just focus on one specific location. What do we do with that data? So this data is then in Plasma Smart, which is our decision-making software. We extract 9,000 physics-based features out of this raw data. So as I said, this raw data represents 200,000 raw data elements per measurement point, which are then extracted into 9,000 physics-based features. These are features like the ratio of peak intensities in the OES, or like the mean temperature or temperature variance in the thermal image, or things like the current RMS value in the electrical signature. And then this data can either directly be fed into a model, or we can reduce it even further into a low dimensional representation. And the same set of data, the same set of reduced data can then be used to train several multiple models. And that is how we are able to derive multiple properties with the same measurement. So there are two main kinds of models that we can train. We can do unsupervised learning, which is on the left, which just shows variations within the sample and comparison across different batches. So this does not really require any calibration. We can, in the raw data space itself or in the physics-based feature space itself, we can map out how similar one batch is to the other. And in the supervised learning space, what we can do is that we can now calibrate models where we connect our raw data signatures to material properties of interest. So the purpose of this study in today's talk, we are going to go over a case study we did with Johannes's group, where we calibrated this data to measure several properties for graphite anodes. And before we go into the case study, just this our vision of where we want PlasmaSense to go to. So this is the same electrode manufacturing line that Johannes talked about in his slides. So all these green arrows up top is where PlasmaSense can be inserted. And so at several stages of the electrode manufacturing process, you can continue to measure these material properties. You can measure different properties at each stage. And what this gives you is a very rich material fingerprint. You have a very rich physics-based material fingerprint that captures how your material is evolving as it gets coated, as it gets calendared, as it gets through the slitting machine. And integrating all of this over several lines of the electrode manufacturing process allows you to build a very rich repository of data that lets you compare variations between different lines, between different factories, and across time. So this will all be enabled by edge compute with sub-millisecond latency. We want to achieve seamless connection with the MES systems, as well as provide both kind of analytics, cloud and on-prem. And then finally, the way we are designing our software, customers own all of their data and they can create their own models. They do not need to come back to SirenOpt to create models for them. So with that, I'll hand it back to Johannes, who will talk a little bit about using the implementation of plasma sense at the Technical University of Munich.
Thank you, Parnika. So yeah, as Parnika has showed, the usage of the tool at multiple stages in the process chain would be beneficial. And at the moment, we do experiments in our dry room. So the equipment and the tool is usable in a dry room, which is already a quite good thing for the battery production. And it was very easy to integrate it in our dry room at the Technical University of Munich. Here on the left side, you can see basically the tool at the moment. So there we have the plasma sensor integrated in this box, and there we put usually the different electrodes or different probes inside. Then we need the gas supply, as Parnika has explained earlier as well. And yeah, it was very easy to integrate it, especially with the help of SirenOpt. Yeah, the commissioning and everything went completely without problems. So we need no major changes in the infrastructure, basically, because you can just plug and play it. The scan time of one sample is around 5 minutes, and it's very simple, especially for the electrodes at the moment to prepare them. So you only need to cut out a little sheet, and then you can put it underneath the sensor and measure multiple properties at once. We have multiple studies ongoing at the moment, including the use case we want to share today. So the first thing we did is we have the multi-property measurement with graphite anodes. These are, of course, one of the easier samples, I would say. And there, the three modes for the data, the optical, the thermal, and the electrical data, are collected with the plasma. We measured multiple properties offline and little one, so the mass loading inline, to actually label the data that we gather from our plasma sensor. We have multiple measurements, as you can see on the in the table on the left bottom side. So we measured, as I've said, the mass loading inline with an ultrasound system, and then we have the porosity, which is used or which is measured offline with picnometer. The average tensile strength, composite layer thickness, interfacial resistance, and the resistivity of the composite volume. So in total, we have multiple measurements of our samples. On the right side, you can see, for example, the measurement of the electric conductivity, which is basically destructive and offline. And on the far right, you can see the adhesive pull off test, which is, as you can see, completely destructive. And you always need to cut out different electrode sections and do the actual testing. And so we usually did these tests to model some properties. And as you can see on the next slide, the first results show already a quite good model performance. So basically, we have had in the early stage already 3 models for the tensile strength there. I have to admit, or I have to say, that the actual labeling, so the actual test itself, has a high uncertainty. This is why there on the left side for the average tensile strength, you see this red bar across the picture. But for the mass loading and the porosity, as you can see, we already achieved quite good precision with absolute or mean absolute errors of 0.3 milligram per squared centimeter and 0.25% of porosity. And for the porosity especially, you have to say that it's very difficult to measure the porosity exactly. So at the moment, the first models performed quite good. We used approximately 80 measurements for each sample. And yeah, we have different technical replicates, which means like locations or technical samples directly close to the sample we used for measuring for the plasma measuring. And it's very interesting that we already achieved these good results. And Parnika will now explain how we even increase our precision.
Sure. Thank you, Johannes. So yeah, as Johannes mentioned, other than mass loading, all of the other properties were measured offline for reference measurements, and we were able to calibrate and get a very good performance with very low mean absolute error across several properties. So this slide focuses on resistive properties now. So the tool used was shown in two slides ago, where it's like a Hioki tool that gives out multiple different resistance values, including sheet resistance and volume resistivity. So what we employed here was a multi-stage modeling approach. So the original modeling approach that I talked about a few slides ago was just use our physics-based features and then use those to fit into, to calibrate a base model and connect that with the final properties. What we can also do here is leverage physics-based relationships. So we know that sheet resistance is related to composite volume resistivity by thickness. And instead of explicitly calibrating or calculating that by assuming a thickness value, what we did is we created a joint model which not only has the physics-based features as inputs, but also the output of the other model as an input. And when we use the joint model, we see that the predictions improve. And a third stage is employed, which is the ensemble model, which just takes an average of the predictions of the base model and the joint model, which reduced our mean absolute error even more. So by leveraging physics-based relationships and employing multi-stage modeling, we can get an even better performance on certain electrode properties. So yeah, that's basically the message of this slide. And so we showed 6 or 7 different properties. And now in this slide, I'm going to show even more use cases for battery electrodes and separators. So this first study shows how different batches of separators show a very different degree of variation. So the image on the right clearly shows you the within batch variation. And this can also be shown in the histograms here, where a tighter distribution is obtained for batch C compared to batch D. So this is the kind of intra-sample and inter-sample variation that can be quantified with the data we collect in the physics-based feature space or in the low-dimensional representation space. This does not require any calibration. The other very important use case we're working on is detection of metal contaminants. As many of you may know, these are killer defects. Small defects as small as 50 microns can lead to thermal degradation of batteries and cause fires. So detection of these contaminants at an early stage, during the electrode coating stage, is super important. And we are actively working on developing algorithms to detect metal defects. So the image here shows how our optical emission spectrometer data changes when a copper contaminant is detected on an LFP cathode. And we are employing this now for real-time detection on battery electrodes for detection of 4 different kinds of metal contaminants: zinc, copper, aluminum, and iron. Roughly the minimum size that we're trying to detect is 50 microns. And this is real data from our tool, again, showing how these outliers are showing up as a deviation from the baseline signal for different. So we have different models for each metal contaminant type. So what we can do is also identify the contaminant and pinpoint the location of the contaminant in the electrode. Okay, so finally, I'd just like to say that in order to realize Johannes's digital twin and complete manufacturing intelligence vision, we need a lot of sensors. We need a lot of non-destructive inline sensors. And PlasmaSense enables that by collecting very rich data from plasma material interactions. So in this slide today, we demonstrated the first 3 stages where we converted the plasma material interactions to properties, defects, and variability. Eventually, as more and more sensors are deployed, we can get to the vision of manufacturing intelligence we want. We want to get to the level of semiconductor industry, and we want to employ these digital twins, employ the closed loop control, and be able to do quality control on supplier materials in real time. And PlasmaSense can enable that. So with that, I'd like to open it up to questions.